Okay, we are live on YouTube. Okay, welcome to 2100. This is going to be your second lecture on proposition logic. For the first part, we're going to do some review of the fundamental concepts. And the second part, we're going to do many exercise problems. Okay, so by now I would have assumed you have read some chapters related to proposition logic, which is mostly in chapter 1 of the textbook. Okay, and then this is going to be a short review, and it's not going to cover all the concepts, but the goal is to help you recollect some of the definitions you have seen so far. Right? Overview, we're going to talk about propositions, truth tables, Boolean variables, logic constants, properties of Boolean operations, and substitution. All right, so what is a proposition? A proposition is a statement that can be either true or false. For example, today is Wednesday. Well, today is Sunday, which is when I recorded this video. So this statement is false. I love CS2100. All right, this can be either true or false. 7 equal to 3, this statement is false. And the following are not propositions. Why am I here? Read the book, because those are the statements that cannot be assigned a value of true or false. Next one, Boolean variables. Oh, by the way, if this is going a little bit too fast for you in terms of video, feel free to pause it. And later on for the second part, you could pause my video and actually try to do some problem on your own before you resume the video. Okay, so all right, Boolean variables. So Boolean variables, well, we typically use letters to represent proposition. For example, the statement or the proposition, today is Wednesday, can be represented by a variable P. And variable Q can represent the statement, it is raining. And a variable, in this case, can take one of two values, true or false. We usually use the letter T for true and letter F for false. All right, so the word Boolean actually coming from someone whose last name is Boole. So in 1854, he published a book called An Investigation into the Laws of Thought, on which are founded the mathematical theory of logic and probabilities. So he approached the topic of logic in a new way, reduced it to a simple algebra, incorporating logic into mathematics. Okay, so and he pointed out the connection between algebraic symbols and those that represent logic forms. Okay, so there is this subfield called Boolean algebra, and now we actually have to study some part of that. And Boolean algebra shows up in computer construction, circuits, and so on. And feel free to read more about the history of Boole in the following link. But since we're going through things topics fairly quickly, feel free to attend the recitation and discussion session to ask your questions, so on. So what is logic operators? Logic operators operate on Boolean variables. So they act like algebraic operations. They're similar to plus, minus, multiplication, and division, similar to as how you operate on numerical values. So just like propositions, operators can be converted into words. For example, the three things that we're going to use most in this class is the logic operator and, or, and not. And it's possible some of those topics are actually a review for some of you, as you might have seen this before. So let's start with the AND operator, okay? So the AND operation is true is if both arguments are true. So again, we're going to use T and F to represent true or false. So in this case, on the right-hand side, what you see here, this is a truth table. So what we do is for each column, it's corresponding to all the possible values of one of the variable, and another column is another possible values for another variable. So in this case, the first column corresponding to the possible values for P, and the second column is all possible values for Q. And the third column is a result of the AND operation. For example, if my P variable is true, my Q variable is true, then P and Q is true. So that, remember, it says that the AND operation is true if both arguments are true. If P is true, Q is false, then the AND operation of P and Q is false because one of them is not true. Similarly, if P is false, Q is true, then P and Q is false. And again, finally, if both of them are false, the P and Q is false. Okay. Of course, if you're doing programming, sometimes the AND operator is denoted by this symbol right here. Okay. So if we go back to say, well, if the variable P represents the statement or proposition, today is Thursday, and then variable Q represent the statement or the proposition, it is snowing, then P and Q means today is Thursday and it is snowing. Okay. Similarly, let's look at the OR operation. The OR operation is true if at least one of them is true. That means in the truth table, if P is true, Q is true, then P or Q is true because at least one of them is true. If P is true, Q is false, then P or Q is true. If P is false, Q is true, and P or Q is true. It's only false when both of them are false. Okay. Again, if you are doing programming, then in programming, you have a special symbol to represent the operation OR. So if you go back to the previously, I have the statement P, statement Q. Then P or Q is today is Thursday or it is snowing. Next is the not operation. It basically negates or flips the arguments. So when P is true, then the negation of P is false. When P is false, the negation of P is true. Okay. Again, in programming, in C++ or Java, the negation has a special symbol. So if the statement P means today is Thursday, then not P means today is not Thursday. So when we have to decide, whether the proposition is true or false, one way to do so is through the idea of a truth table. The truth table enumerates all possible relationships among the truth values of the proposition variables. For example, in this case, this is a fairly complicated proposition that involves variable P and Q. The idea of it is to create a truth table with columns where columns represent different parts of the proposition. And then you can do this in a hierarchical way. For example, the negation have the highest priority while the OR has the lowest priority. So if I want to break the proposition here into different chunks, what I can do is I can say, well, obviously I have my variable P in this proposition. So let's write it one more time. P or Q and negation of P or Q. Okay. So because it's involved two variables, so we are going to say the first two column is variable P and variable Q respectively. But then notice there's a first piece right here, which is P or Q. So therefore, I need to decide what is the truth value of this. There's another piece here that is negation of P. So we put negation of P here. And of course, the next level is negation of P or Q, which is what we get here. And finally, the last column is the entire proposition. Okay. So of course, how do we do this? Let's say we start with the first column and the second column where we look at all possible combination of values for P and Q. We know that since each variable has two possible values, then I have a total of 4 different combinations. That is when both P and Q are true, when P is true, Q is false, when P is false, Q is true, or when both of them are false. Okay, so that's corresponding to the first column. But now let's do it one row by row. Okay, so assuming for the time being, I have not decided what the value is for the remaining columns, but we can do this by doing a quick practice run. So because I'm setting P to be true, Q to be true, then P or Q is going to be true, because if I decide on an OR operation, if one of those variables is true, the OR result is true. Now, because P is true, the negation of P is false. And now, because negation of P is false, I need to understand the negation of P or Q. But because Q is already true right here, then negation of P or Q is always true. Now I have decided for each of the little parts of the proposition, for example, P or Q here, based on this row, is true. And then negation P or Q here, this is also true. And now I have, in order to get the truth value for the entire proposition, I have true and true. Therefore, I have true. Later on in the practice problem, we're going to do more of those exercises. But similarly, you can fill the truth table for the remaining columns, starting from the setting of the first two columns. Okay. So the next concept is called logic equivalence. Two statements are said to be logically equivalent if they have the same value for every row of the truth table. And then there's a very important concept that you're going to use. It's called De Morgan's law. So what does De Morgan's law do? It says that if I have a pair of variables P or Q that is connected by the OR operation, if I take the negation from the outside, this is logically equivalent to bring the negation inside and flip the arrow. So change the OR operation to an AND operation. One way to really remember what does De Morgan's law does, if you put the negation on the outside, you kind of flip the OR operation, which is like, a regular V, back to an upside down V. Okay. The same thing for the second part. If I have a pair of variable P and Q, if I put a negation on the outside, this is logically equivalent to bring the negation inside, but flip the direction of the arrow like this. So the question is, how do we prove this? How do we prove that the left-hand side and the right-hand side is logically equivalent? So I will give you a hint, and this is something you could practice. You can say, I'm going to build a truth table, P, Q, and P or Q, and I'm going to have the negation of P or Q. I'm going to have also negation of P, negation of Q, and negation of P and negation of Q. And then you're going to do all the possible combinations. And what you can see is, as you fill this truth table row by row, at the end of it, what you're going to see is this particular row that involves the left-hand side, and then this particular row involving on the right-hand side is going to have the same truth value for every single row. So this will be an interesting take-home practice for you. And later on, we're going to do more practice surrounding this kind of problem. Okay. All right. So there's a few logical constants, right? There's two. One is called tautology, which represent by T. This is a proposition that is always true. A contradiction with the variable C is a proposition that is always false. So let's give an example. If I'm thinking about a variable P and a negation of P, the statement is that the P or not P is logically equivalent to tautology, which is to T. What does this mean? This means this statement on the left is always true. okay? So why is that the case? Again, what you can do, you can draw a truth table, P, negation of P, and P or negation of P, okay? So if I want to fill out this truth table, what would I do? I would say, okay, there's two variable values P can take, either true or false. If P is true, then negation of P is false. If P is false, negation of P is true. And now I have P or negation of P. What I get is going to be true or false, which is true. Now, the second row at the very end is false or true, which again is true. So what does this mean? The statement is always true, so it's equivalent to the tautology. Equivalently, you can also do a small take-home exercise. You can see that P and not P is always false, okay? So because if P is true, not P is false, then P and true and false is always false, okay? So now remember in the previous example, we want to say, can you show the statement P or Q combined with through OR operation minus P and minus Q is a tautology. If I want to prove it's a tautology, I want to prove it's always true. So what do we do? In this case, I'm just going to fill the truth table. So let's start from the first row. When both P and Q are true, then P or Q is true. And if P is true on the first row, then negation of P is false. And Q, negation of Q is false. Then negation of P and negation of Q is also false. Okay. But now I need to decide on the last column, which is P or Q combined with negation of P, negation of Q. So this is actually equal to, in some sense, this is true or false, which is equal to true. Okay. So that's our first row. Let's continue with the second row. When when P is true, Q is false, then P or Q is true. Negation of P is false. Negation of Q is true. And so fourth and fifth column, if I use AND operation, that's false. But because P or Q is always true, the last thing is always true. Now, the third row, which is very similar to the second row, P or Q is true. Negation of P is true. Negation of Q is false. Negation of P and negation of Q is false. But because P or Q is true in here, the last one is always true. Last one, both of them are false. So P or Q is false. But negation of P is true. Negation of Q is true. So those two, negation of P and negation of Q, that is true. So because the second part of the statement now is true and it's an OR operation, that means the whole statement is true. So now the entire fourth column, everything is true. That means this is a tautology. Okay. So this is just a repetition of what I just did. Theorem 2 is going to be your best friend to try to solve problems in this chapter. So there is a sequence of properties associated with Boolean operations. And it's essentially break down to a collection of logical equivalences among propositions. Okay, let's go over one by one here. And this is the one that's going to take a bit time. Let's start from the first one, commutative rule. What does this rule say? It says if I have two propositions, P and Q, P and Q is equivalent to Q and P. So what does this mean? This is saying that if I switch the order of those two propositions in the AND operation, the result does not change. Similarly, if I have P or Q, that is equivalent to Q or P. Again, what it is saying is if I switch the order of the OR operation between the two variable P and Q, the result does not change. So that's the first one. Now let's talk about associative rule. If I have three variables, P, Q, and R, if I do P and Q first, N and R is equivalent to do Q and R together with P. So again, if I have three variables, the ordering of how we're doing the operations among them does not really matter. So this is associative rule. Similarly, you have associative rule involving OR operations, okay? Now, I must say that one of the most important rule among all this is actually distributive rule. And this is a rule where students sometimes makes mistakes because how this is designed. So have to be very careful, but once you can use it, it actually can help in a lot of situations where try to prove logic equivalence. So what does distributive rule say is to say, well, if I have Q and R, or Q or R as operation with a P on the outside, if we want to distribute the operation by bringing P inside, so essentially P and the OR of QR is equal to P and Q or P and R. So maybe another way for me to highlight the operations is that if there's an OR operation, when I do distributive computation, I bring the OR operation on the outside. And if I have this AND operation, I bring in each of them inside, okay? And similarly, you have AND operation that is inside the parentheses. When you bring P inside, this, is the one that's connect the two pairs, and then this OR operation of this, okay? So again, when you actually try to prove logic equivalences, those are the rules that you're going to use quite a bit. The next thing is called identity, which means if you can treat the tautology T as essentially an identity variable. So if P and T is always P, so the truth table of P and T only depends on P. Now, if P or C, which is contradiction, again, the truth table is always related to P. So P or C is logically equivalent to P itself. Negation is quite interesting. If I have a variable P and a variable not P, if I take an OR operation, we know that is equivalent to T, and P and not P is always equal to C, which is contradiction. Double negation, it's almost one way to remember double negation. It's almost like English language. Not put another not on the outside is positive. So not and not P is P itself. The next one, well, P and itself is equal to P. This is De Morgan law I just went through. Again, the most important part of De Morgan's law is that if I put the negation, it changes the direction. When you bring the negation in, it changes the direction of the operation. It goes from, pointing up to pointing down, and from pointing down to point up. So this is another rule. There's also a universal bound, which is saying that, if I take an AND operation with any contradiction, it's always a contradiction. If I take an OR operation with a tautology, it's always a tautology. Absorption is a situation where if I have essentially duplicated variable P in a statement in this following form, is equivalent to the logic truth table of P itself, okay? And similarly here. And of course, if I negate tautology is equal to contradiction, negation of contradiction is equal to tautology. That's the last one. Okay, so this table will show up in many places when you're actually going to try to prove logic equivalence. You can typically look it up, but for the actual exam, it would be a nice thing for you to review. Okay, so we're going to go through some examples. So there is what's called substitution rule. Once you have theorem 2, as stated here, you can replace any expression on the left-hand side of the symbol logical equivalence with expression on the right without changing the truth table because they're logically equivalent, okay? Very important part to prove logical equivalences from left to the right is do not skip steps, especially do not skip commutative or associative rules, right? Okay, so in this particular example, if we want to prove from left-hand side to the right-hand side, the first step we do is let's start from left-hand side, okay? From the left-hand side, I have this statement, but I could use commutative rule by switching the ordering. So this is what you get. And once you get the statement on the right, you can just apply absorption to get P, okay? So in this case, when I'm trying to prove logic equivalence, I just apply the two rules. One is a commutative rule, one is absorption. If this is too fast for you, I would say this is a time to pause the video for 1 minute or for 2 minutes and just try to solve this on your own. Okay, so this is it for the first part, and it's a quick review of some of those concepts you might have already seen by reading the textbook. For the second part of the lecture, we're going to do many practice problems.